Hello everybody, this is Professor Lombardo. The video today is going to go through a couple of examples of how to find the middle, say 90% of scores associated to a sampling distribution. This is a very important step in working towards the statistical technique called the confidence interval. So it's a very nice intermediate step, and it uses a bunch of techniques and tools we've already developed. It'll reinforce our understanding of what a sampling distribution is and how to apply the central limit theorem, and it'll review a process for finding the middle k% of a distribution as well. Okay, so let's get started. Here's a typical setup or a typical statistics type of problem that you see in a textbook. You can assume, suppose you're designing an elevator, you can assume that the weights of human beings typically have a normal distribution. And let's, for the purposes of this problem, say that the mean weight of a single human being is 160 pounds, and the standard deviation will be 30 pounds. So we'll expect to see some variation from that mean a little bit, and we quantify that variation using a standard deviation. All right, so if we use like our z-score usual range of scores, anywhere from 100 to 220 pounds would be a usual weight for a human being, according to this particular model. Now, when we're designing an elevator, typically humans don't travel one at a time, right? So a typical elevator has a maximum of 15 people allowed at a time. And assuming that we randomly select 15 people from our general population, right? So 160 pounds mean, standard deviation of 30. If we're assuming we select 15 random people from this population to get on the elevator, it's a good idea to know what are the range of weights for that middle 90%. And we're looking here in particular, we're going to start by looking at the mean weight for this group of people. So a couple of things to notice. First, notice that we are talking about a mean weight for a sample of size 15. Okay? So we're not talking about the weight of one individual, where the mean would be 160 and the standard deviation would be 30. We're talking about the mean weight for a group of 15 people. Okay, so this is naturally a central limit theorem problem. Okay, since our original population is normally distributed, we don't have to worry about having more than 30 people in our sample size, so we can apply our central limit theorem right away. Essentially, what the central limit theorem implies is that, first of all, let's call x bar, which is the mean weight for a group of 15 people. This is normally distributed. Moreover, we know that mu of x bar, or the mean of this x bar, is going to be the same as our original population. So this is still going to be 160 pounds. The standard deviation of our mean weight, or our sample mean, is going to be our original standard deviation divided by the square root of our sample size. So in this case, this is going to be 15. So all we've done at this point is applied the central limit theorem in these three steps. Now we can actually quickly use Excel to figure out what this 30 over the square root of 15 is. So our sampling distribution should have a standard deviation of 7.7, let's say 7.5 if we round up. Okay, so the mean of our sampling distribution is 160. The standard deviation of the sampling distribution is 7.75. Okay? Oops, we want less precision here. Okay, so we'll use 7.75. Okay, so we know it's normally distributed, right? We know exactly what our mean is, and we know exactly what our standard deviation is. So essentially what this means is that norm.dist can be used to answer questions about probabilities involving x bar, this random variable. All right? Similarly, we can use norm.inverse to answer questions about our percentiles, or to move from a known probability to a score. Okay? So we'll do this one afterwards. But here's the idea. Here's what we want to do. We want to use our usual process with these parameters to find the middle, in this case 90%, for the random variable x bar, which is really just the mean weight for our 15 people. Okay? So the process is exactly the same as we've seen before, right? The k value in this case is 90%, which means our alpha is going to be the remaining 10%. We have to split that alpha over two tails in our normal distribution. And then the next step is we want to figure out what is the z alpha over 2, or the special z-score that has an area of 5% to the right, or in other words, an area of 95% to its left. Okay, so keep in mind z alpha over 2 has an area or a probability of alpha over 2 to the right, or 1 minus alpha over 2 to the left. So in our case, if we quickly compute what is 1 minus our 5%, this is going to be our area to the right, or sorry, to the left. So to compute this z-score, we use norm.s, because it's a z-score, that inverse, because we're plugging in a probability to get a score. We'll put 0.95 because it has to be left-hand area, and this tells us exactly which z-score we're going to use. Okay? So the next thing we determine is our margin of error. The general formula for this is our z alpha over 2 times our standard deviation. But keep in mind, this standard deviation is not referring to 30. It's not referring to this 30 pounds. It's not the standard deviation of our original weight distribution. It's the standard deviation of our sampling distribution. It's how much we expect our mean weight for 15 people to vary. So in this case, we're going to be using the 7.75. Okay? So I'm going to take my z alpha over 2, which is about 1645, or in this case, you can just cell reference it. And since I also computed my standard deviation for the sampling distribution in a cell, I can cell reference that at all. So I'm just taking 1.645 times 7.75. This gives me my margin of error. Okay? So now we can finish the problem because we know our margin of error. Just move this down a little bit more, give ourselves some space. All right, so now we can finish our problem because we know our margin of error. All right, so the middle 90% for our sampling distribution, which is the distribution for our mean weight for 15 people, is between, on the one side we'll have mu x bar, so this is the mean of your sampling distribution minus the margin of error. And then on the right-hand side, you have mu x bar, the mean of your sampling distribution, plus that margin of error we just computed. Okay? So we can put these two things together pretty straightforward, right? The mean of our sampling distribution is 160, right? This is what doesn't change. The mean of your sampling distribution is the same as your population. What does change is your standard deviation. So our margin of error over here is our 12.74. And then here, we would take our mean, which is 160, and add our margin of error. Okay, so we would expect between 147 and 172, this is where the mean weight for our 15 people would actually fall. Okay, does this make sense? So just in words, what's going on here is, we would expect roughly 90% of the time, right? Our probabilities are sort of centered around the mean. So we would expect that the mean weight for the 15 people, right? If we took all their weights, added them up, and divided by 15, the mean weight for those 15 people typically would fall between 147.3, let's say, and 172.7. Okay, so this is the middle 90%. This is sort of like the 90% of where we're pretty sure that our values are going to fall. Okay? Slightly different problem works with the total weight. Okay, so how do you deal with the total weight of this group of people? Notice that if we're talking about the total weight for 15 people, this is going to involve a group as well. It's a group measurement, but it's not the group mean. Okay, so it's not the same as X bar. But here's the idea. If you know what the mean of a group is, you also know what the total sum is going to be. Okay, so here's our general idea. Find the middle 95% for X bar. That's going to be our first step. Then multiply these values by 15. Okay, and that's going to give us the middle 95% for the total weight, because in general the mean is going to be, your first guy plus your second guy, etc. ... x out to your 15th person divided by 15. And if you'll notice, the relationship here, the mean is just the total divided by 15. So if we can find the middle 95% for the mean, multiplying by 15 undoes that division and gives us the middle 95% for our total. Okay, so here's how we would do this. Typical problem. We're dealing with a group of people. Let's still assume we're working with 15 people, so I forgot to put that in. So we're working with this group of 15 people. All right. Since we're working with the mean of a group, we need to apply the central limit theorem. All right. So once again, we're going to end up with the same parameters. So I'm just going to copy and paste this down here. All the work is exactly the same. Central limit theorem is going to tell you, sorry, that didn't copy and paste. All right, so the central limit theorem for X bar, which is the mean weight for this group of 15 people. Central limit theorem says this X bar is normally distributed. It has a mean of 160 pounds and a standard deviation of 30 over the square root of 15, which in our case we computed was our 7.75. Okay, so the parameters here haven't changed. What has changed is, first of all, how much of the middle we're considering. We're now considering 95% of that middle range. And we want a total weight, so eventually at the end, to get that total weight, we're going to do this step where we multiply by everything by 15. Okay, so let's first start out by finding the middle 95% for X bar, for the sampling mean. Okay, so our K in this case is 95%, which means our alpha is equal to 5%. Which means alpha over 2 is equal to 2.5%. All right, now z alpha over 2 is going to be the z-score with an area of 1 minus 2.5% to the left. All right, so in other words, 0.975 is to the left. So we use our normal approach. Norm.s.inverse, right? This goes from a probability to a score. The left-hand probability we plug in here is 0.975. And since we use the .s, we make sure that we're getting a z-score. Okay? Our margin of error is still just going to be the z alpha over 2 times our standard deviation of X bar. So in this case, we're still using z-score times the standard deviation of our sampling distribution. So this won't change either. You'll notice that, oh wait, it will change because our z alpha over 2 changed, sorry. Okay, but the standard deviation piece we used didn't change. Okay, so this is our margin of error. So the middle 95% for X bar, for the mean weight of these 15 people, is, once again, it's our mean of that sampling distribution minus margin of error out to mean of the sampling distribution plus the margin of error. So in other words, this is going to look like 160 minus our cell reference margin of error, and then 160 plus our cell reference margin of error. Okay, so we just found the middle 95% for the mean weight. Now keep in mind the relationship between the mean and the sum total of the individual weights. So the total, the x1 plus x2 plus x out to x15, so the 15 individual weights divided by 15 gives us the mean. So in other words, if we took 15 times the mean, this would give us our total. All right, so we're going to use this relationship to transform the middle 95% of the mean weight for x bar into the middle 95% for the total weight of the group of 15 people. All right? All we do here is take 15 times the lower bound for the mean weight, and then we would take 15 times the upper bound for the mean weight. And now this ends up being the middle 95% for the total weight of the group. All right, let's round these to make them look a little nicer. Oops, wrong direction. So here's the idea. If we have the underlying assumption that the weight of a single human being is normally distributed with a mean of 160 and a standard deviation of 30, right? Now, as elevator engineers, we know that the middle 95%, so the 95% we should kind of expect to see for the mean weight in a group of 15 people is going to be between 144 and 175. But we want to know how much weight should we design our elevator to accommodate. So the middle 95% for a total of a maximum group of 15 people should be anywhere between 2,172 pounds and 2,627 pounds. So looking at this, we would be fairly safe to design our elevator to accommodate a total weight of, let's say, 2,630, right? So we're just going to take a look at this and kind of round up to the nicest value. So this would, if our elevator could accommodate 2,630 pounds, then we should be relatively safe, right? We'd have a confidence of about 95% that a group of a maximum size 15 shouldn't be pushing our maximum weight, okay? So that's one use for why you might want to know the middle 95% for the total weight. And again, the only difference here is to get from the total, we just took the number of people in our group times the mean weight. So if we have a middle 95% for x bar for the mean weight, right? Just multiplying each one of those boundaries by 15 gives us a new middle 95%, but for the total weight of the same group.